Okay, so metallic ions, metallic compounds. They're not really a compound, as I just said. They just kind of hang together. All these little nuclei, these are all metal atoms, and their electrons just kind of go in between them, not calling anyone a home. They're all what we call delocalized. They just move about. Okay? Quick video. It's a fun video. I like this video a lot. It really explains metallic bonding, which there's really no metallic bonding, but it kind of looks like that. Okay? So, I know, I'm not quite sure where half of it went.
In this video, we're going to talk about metallic bonding, and then we're going to use our understanding of metallic bonding to explain some of the characteristics of metals. We already know that metals are solid, they're hard, they conduct electricity and they conduct heat, and then they're also malleable and ductile. In other words, they can be shaped and molded and dented. So why do metals look and act this way? Well, it all comes down to how the metal atoms are bonded to each other. Bonding is all about the electrons. Whether we are talking about ionic, covalent, or metallic bonding, it comes down to what the electrons are doing. The electrons in metallic compounds are uniquely able to travel freely throughout the entire compound. Kind of like the idea of a big event, like a sporting event. And if you've been to one of these, you may have seen somebody toss a beach ball up into the air, and you've seen that batted around as all the people kind of hit that beach ball all over the place. It just moves randomly all over the place. This is kind of like what the valence electrons of a metal atom are doing. If you can imagine that all the people here in the stands represent a metal atom, and this beach ball is representing the valence electron of one of these metal atoms. It just can move randomly throughout the entire stadium. Now, a bit of a better representation is if you can imagine if everyone were to bring a beach ball, at least one, because metal atoms usually have at least one valence electron. And if all of these things are moving around randomly, you can imagine it would get pretty chaotic. But that's kind of the idea of metallic bonding. All of the atoms are going to share those electrons all the way throughout the substance. Now, if you were looking up from the field, you may not even see any of the fans at all. You just see beach balls moving all over the place, almost like a sea of beach balls. And this is what scientists call the electrons in the metal atoms. It looks like a sea of electrons. It's just kind of moving all over the place. And so the electrons are just free to move all over. And you can see in red here, we have our metal cations. You can see these things right here, the metal cations. And then we could also say that the electrons are delocalized. And this word just means that the electrons are kind of free to move throughout the entire compound. Now, this sea of electrons can allow us to explain some of the characteristics of metals. Let's just start with the fact that metals can conduct electricity. So electricity is defined as flowing electrons. And when we have a power source like a battery here, the electrons are going to flow through a wire or something in one direction. And they'll just continue to move. In a circuit, we actually call it an electric circuit. It's kind of like going back to our stadium idea. If there was a big gust of wind that would come through and blow just in one direction across the stadium, you can imagine that all these beach balls would start to move all in the same direction across the stadium. And that's how electricity works.
That's a really good analogy of how electricity works.
The only difference here is that in electricity or electric circuit, the electrons would continue to be added to this side of the circuit, and so we would never have an end to those electrons as long as we had a power source. One other property that this sea of electrons can help us to explain is the fact that metals are going to be ductile and malleable. In other words, they can dent them. And so if we can hit this metal here with a hammer, those cations there you see in red would be able to slide past each other, but they wouldn't be able to slide too far because these seas of electrons, all these electrons here, are still going to hold them in place pretty well. So it keeps them solid, but gives those atoms a little bit of movement. And that's metallic bonding and some of the properties of metals.
So metals, again, their electrons their valence electrons just tend to roam. They're so loosely held, they just move around all the nuclei. And then the metals themselves have this crystalline structure to them. This is all the nuclei and how they line up. And they're very compact and they're very orderly. We say that they're like, face-centered or center face-centered or square face-centered. But there's certain crystal structures that are just unique just to metals. And I kind of like this little, all these grapefruit or oranges, whatever it is here, because you can see like the little spaces in between, and that is where the electrons would be. The electrons would be in those little spaces. Okay? Now, here's how I picture metallic bonding. And this, I saw this one day and I went, that's what a metal bonding would look like. You guys ever play with foam? It's like gack with little styrofoam balls in it, like little beads. Well, I vision these little styrofoam beads as being the metallic nuclei. And the gack, the blue stuff, are the sea of electrons. Okay? Do you see how the sea of electrons are around all the little nuclei, little white balls? Yes? What's so nice about this, you can stretch it. And as you stretch it, it stays together. They're still attracted to each other. That gack is keeping everything together. Those electrons are still attracted to those nuclei, so you can pull it out, making wires, stretch it out, and it stays together, just like a metallic bond would. And eventually it would break because it gets so thin it would eventually break. Just like metals do. If you take a wire and you keep pulling and pulling and pulling, it's going to break eventually. It's called tensile strength. I think some people say tensile, but it's like the tensile strength of this wire. They put little clamps on it and they literally just pull it and pull it and pull it to see when it breaks. So eventually it will, but this is what metallic bonds actually look like. Or you can shape them. Shape it into a ball. You know, here's all my green electrons, and the little white beads or balls show those are the nuclei. Does that make sense? And then, of course, you can shape them into beautiful things like this, which I could never do. Or, and this is my favorite, the unicorn. Who took the time to do that? That's just amazing. Just amazing. But just like metals, you can shape that foam into all kinds of different things. Okay, and they stick together, but they're only attracted to each other because of the gack that keeps them together. It's what the electrons do too. You good? Okay. Now, there are really no such thing as metallic compounds, metallic bonds. It's more of a mixture. Metals tend to interact as mixtures, and these mixtures are called alloys. An alloy is a mixture of two or more elements. One has to be a metal. And these alloys are stronger, more durable, less corrosive than the original individual metal. For example, like sterling silver up here. Most jewelry, if you wear silver jewelry, you're not wearing pure silver. You're probably wearing sterling silver. Sterling silver is mostly silver with some copper in it. That copper gets in between those nuclei, those little positive spaces in between the nuclei, and actually shores it up. It makes it harder. It keeps it from corroding. When I, years ago, 30 years ago, I bought my family home. They've lived in it since like 1820 or so. It's a really old house, but when my aunt went to assisted living, she just sold me the house and everything in it. She just take everything, I don't care. I'm like, well, most of it wasn't, great stuff, but okay, whatever. But when we moved to Westchester, we finally had to start cleaning things out. And I found this old desk in the garage. And I was going through the drawers, seeing what was in there, some old cool stuff. And I opened this one drawer, and there was this thing in there. It was black and sticky, almost like someone had dipped it in tar and put it back in the drawer. It was like, ah. So I went and got some gloves and picked it up. It was solid, and I tossed it into the dump. It was a small dumpster. And I heard ding. I'm like, that was metal. I wonder what it was. So of course I get in the trash can, I pull it back out, and I take some vinegar on paper, I got a rag, and I rub over it. It is pure silver underneath. It was a pure silver bowl. But silver reacts really well with the air and oxidizes and turns that black, tarry, sticky material. And that's what it was. But if it was been sterling silver, that never would have happened. So I cleaned up the bowl and got it all unstickied and put a wax on it to keep the air from getting too close to it. I mean, it's not a pretty bowl by no means. It's got pock marks in it and scratches and where the oxidation did the damage. But it's still kind of neat. I mean, it's like, this was all, I would never have known this bowl was even there if I wouldn't have tossed it in that big trash can and heard it go tink. I went, no way. So it was very cool. But that's what happens. If you don't have alloy, if you don't have something to make it stronger and less corrosive, it's going to be soft and corrode and things like that. Real gold is really soft. You don't wear real gold around your neck. You wear a certain carat type of gold. Now, I had a friend named Rajiv who used to go to India to see his family, and he came back with real gold all the time. He liked these really gold necklaces. And he always called me Maggie. And say, Maggie, do you like my necklaces? I'm like, yeah, Raj, they're really nice. And they weren't necessarily, they were pretty in a way, but they looked like gold. They just didn't have that nice shiny appearance, and they were really soft, and they broke a lot. So, we harden gold up with probably silver or copper or something else. But so here are some of the different common alloys. Cast iron, which is also steel. They put some carbon in it to make it stronger. Stainless steel, most of your cooking ware and things like that. It has some chromium and nickel and carbon in it, just to make sure it is nice and strong. Okay? When you're cooking in it, you don't want it to melt away into your food, right? Okay. This is a quick video on alloys. I like it. It's kind of fun.
In this video, we see how different metals bond together to form alloys, which still retain the metallic properties of the starting metals, but are usually stronger. Metal atoms are typified by having only a few electrons in their outer shells. This means that even when they bond, there's always room in this valence shell for more electrons. Each metal atom can bond with up to 12 others in a close packed lattice. Look at the red atom. It is surrounded by 6 in its plane, and 3 on top and 3 underneath. A less compact crystal structures are possible too. For example, this arrangement, where each atom is bonded to 8 others. Because there are still not enough electrons to complete the outer shell of any of the atoms, the electrons can move easily from one atom to another, making metals good conductors of both electricity and heat. And because the electrons are not localized in fixed bonds, the atoms can slide past each other, making them ductile, allowing the metal to change shape. It also means that when you try to react metals together, the atoms normally just mix into the lattice, forming metallic bonds with each other, and with no fixed proportions and randomly distributed. These structures are called alloys. Contrast this with compounds between metals and non-metals, or between non-metallic elements, where the proportions of each element is fixed. The oldest example of an alloy, perhaps, is the way bronze took over from copper in the early human communities of Europe around 6,000 years ago. During the late Stone Age, axes began to be made of pure copper, but they were fairly soft. When small amounts of tin were added to make bronze, you got an axe which was twice as hard and worked well. The Bronze Age had arrived.
Woo!
The atoms in a metal lattice are held by non-directional bonds, a sort of sea of loose electrons, as we said, allowing the atoms to slide past each other, still touching, making metals relatively easy to melt and bend, but hard to vaporize. When metals change shape, atoms actually slip over each other like this. However, this process does not happen all at once, but bit by bit, rather like trying to move a carpet by putting a ruck in it. Here is the way it happens in a metal. You see the slip moving easily one atom at a time, where there's a dislocation in the lattice. It is this easy movement of atoms in the crystal lattice that makes most pure metals soft. Now put a smaller or bigger atom into the lattice, and this easy movement of the dislocation is blocked. See the way the bigger atom stabilizes the dislocation, which gets no further unless you put greater force, meaning that it's harder to bend the alloy. To finish, let's look at some well-known alloys. Bronze, 3/4 copper, quarter tin, for sculptures, boat hardware, screws and grill work. Brass, 70% copper, 30% zinc, musical instruments, coins, door knockers. Carbon steel, 99% iron and up to 1% carbon for building construction, tools, car bodies, machinery, rails, etc. Stainless steel, iron with about 18% chromium and 8% nickel, used for tableware, cookware, surgical tools and so on. Aluminium alloys for planes contain a few percent of copper or other metals. Amalgam is mercury with silver and other metals once used for dental fillings. Solder, lead and tin for joining electrical wires and components, melts very easily. Gold is usually an alloy containing another metal such as silver for increasing hardness. The number of carats, K, defines how many mass parts of pure gold are found in 24 parts of the alloy.
Okay, so fun little things about alloys. Any questions about the alloys? We used to do a lab called the brass penny, when actually it was we called it the gold penny lab, but it's really a brass penny, where we took a penny and we coated it with zinc, then heated it up and turned it into brass. But this process is really nasty. You have to heat up sodium hydroxide with zinc, and really the only place you can do it is under the hood. And we tried so many times to do it in different ways, and it's burdensome, and it's really dangerous, and it burns your nose, your mouth. It's like having drain cleaner vaporized in this room. So it's not, and for the outcome, it's fun to have a brass penny, but it's a lot of work and it's pretty dangerous. So we just kind of stopped doing it. But I still left the picture up there so you can see how we mix the copper and the zinc to make brass. Okay? Any questions on alloys or metals? No? Okay, now we're going to go into more of bonding. So we'll talk about bonding today, then we'll do naming acids on Monday, and then we'll probably come back to the bonding stuff on Tuesday, or maybe on Monday if we have time. Okay? So, I like this. You have a joke about covalent bonds? Do share. Someone laughed. Thank you, Griffin. Thank you. Get it? Covalent, they share electrons. Okay. Anyway, molecular formulas. Make sure you write this stuff down, please. Molecular formulas. Molecular formulas basically are the things you've been writing already. They're formulas that tell us what elements are present and how many of each, how many atoms of each element are there. So it describes the compound by telling us the element and number of atoms of each element. That's what subscripts tell you. The number of atoms. So if it says C6H12O6, that means we have 6 carbons, 12 hydrogens, 6 oxygens, right? So that is what a molecular formula is. You've been writing these when you crisscross your charges and you make formulas. Yes?
Like glucose?
Yes. Very good. Okay? Structural formulas tell us a little bit more. Even though molecular formulas are good, they don't tell us something about the molecule or compound we need to know. How is it structured? The structure plays a role in its properties. So a structural formula is going to tell us not only the atoms and how many are in there, but it's also going to tell us what's connected to what. That is very important. So it tells us how they're bonded and what kind of bond is also formed. Is it an ionic bond? Is it a polar covalent bond? Is it a non-polar covalent bond? We'll look at that next week. Okay? So these are the different types of formulas. You know the molecular formulas. That's what you've been writing. These are structural formulas. See how we can show the nitrogen is in the center and each of the hydrogens are coming off the nitrogen? That's a structural. If you take any college courses, you'll have to do perspective drawings. Because you've got to remember, this molecule is not two-dimensional, it's three-dimensional. It's got an X, a Y, and a Z axis it lies on. Okay, and because of that, you need to have a perspective of how these atoms and how they're arranged and how they come out towards you and things like that. We will make ball and stick models. That's kind of an easy way to see a perspective of what this thing looks like in a 3D model. But space filling, this is probably the most accurate because they don't have like these little lines between them. They overlap each other's valence shell. So the space filling is probably the most accurate of the diagrams we can look at. But we'll do these and these. Okay? Okay, so there are several different types of covalent bonds we're going to talk about. Do not worry about the fourth one on there. Do not write down coordinate covalent bonds. We're not going to do those. But we'll talk about single, double, and triple bonds. Single bonds are shown through a sharing of valence electrons. It's hard to show that, so what we use are our Lewis dot diagrams. Remember the ones we made last chapter? So we're going to use our Lewis dots, and they're going to show us the bonding pairs of these electrons and how these structures are coming together. So for example, if you look up here, let's say I have CO2, carbon dioxide. Carbon has how many valence electrons? 4. Thank you. So carbon has 4 valence electrons. 2, 3, 4. Okay. Oxygen, I'm going to get rid of this top part here, just make it easier to see. Oxygen has how many valence electrons? 2. 2? 6. Thank you. 6. Okay, so I'm going to put an oxygen on this side. 1, 2, 3, 4, 5, 6. I'm going to put an oxygen on this side. 1, 2, 3, 4, 5, 6. Now the goal is to have 8 electrons around each of these elements. They all want an octet. They want 8 electrons in their outermost shell. So right now, if I look at it, oxygen has 1, 2, 3, 4, 5, 6, 7. Not good enough. Carbon has 1, 2, 3, 4, 5, 6. Ugh. And this oxygen has 7 as well. So we look and say, okay, what can we do? Well, this carbon, let me open these up. And this carbon takes this electron and moves it here. And oxygen takes this electron and moves it here. Now I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 electrons now around this oxygen. Yay! I've got 1, 2, 4, 5, 6, 7 around that carbon. So I'll do the same thing. I'll move this electron up there and this electron, whoops, this electron here and this electron here. Now if you look, 2, 4, 6, 8. Carbon has 8, 2, 4, 6, 8. Oxygen has 8. We can use these Lewis dots to help us understand how these things are going to bond together. That's why you need to understand Lewis dots. That makes sense? They're easy to work with. What we typically do is I will give you a bunch of bingo chips, and you can just rearrange them. You can move them around pretty easily until you get your 8 electrons around each of the elements. Hydrogen wants 2 though. Hydrogen doesn't need 8. A bond is like a handshake between two people. We're bonding right here, okay?
We did.
Yeah. We're not just standing side by side. We're handshaking, okay? It's got to come from each of the two individual atoms, okay? Does that make sense? Okay, good. So, the single covalent bond is our first one we're going to talk about. Single covalent bond is when they share one pair of electrons. For example, if I have NH3, nitrogen has how many valence electrons? 5. So we put 5 valence electrons around it. I know where they're going to go, so that's why I placed them the way I did. And each hydrogen has how many? 1. Thank you. So 1 hydrogen there, 1 hydrogen there, and 1 hydrogen there. So now you can see nitrogen has 8 electrons around it, and each hydrogen has 2. But we don't like to keep them like that. The dots are a little cumbersome, aren't they? So we get rid of the dots, and we draw lines where a pair of dots are. Make sense? Yes? Goodness. Let's tape it. Okay, so does that make sense what we're looking at right there? These are called unshared pairs of electrons. They're unshared pairs of electrons. Yes? Because they're not shared with anything. Then we have double covalent bonds. Double covalent bonds are the sharing of 2 pairs of electrons. So if I have CH2O, carbon has how many valence electrons? 4. So I put my 4 valence electrons up there. Each hydrogen has how many? 1. 1 hydrogen there, 1 hydrogen here. And oxygen has how many? 6. Again, 6. So there's oxygen with its 6 valence electrons. Now I went ahead and set them up like this because I know that's what it has to end up looking like. I can't get them to like animate and move on Google PowerPoint. So, but in order to get 8 valence electrons, get an octet for each of these, I have to have a double bond there. Make sense? So I get 8 electrons here. I get 8 electrons here, and each hydrogen has 2. And move this back a little bit. Doesn't want to go back. There we go. And dots drop out, and we have single bonds between the carbon and the hydrogen, and we have a double bond between the carbon and the oxygen. They are sharing 2 pairs of electrons. So this is 4 electrons here and 2 electrons for each of those. Yes, sir?
Would the unshared dots still be around that oxygen?
They should be, yes.
Right.
They got dropped somehow. Yes. But yes, you always want to leave your unshared pairs because it affects the shape of the compound, of the molecule. And because of that, it reacts differently. And we'll talk about that on Tuesday. Okay? Now, triple bonds. C2H2, we have a carbon. How many valence electrons? 4. Thank you. 3 and 4. Another carbon here with its 4 valence electrons. And each hydrogen has what? 1. They like symmetry. These molecules like to be symmetrical. So now I have 2, 4, 6, 8 electrons around this carbon, 8 electrons around this carbon, 2 around the hydrogen. We drop the dots. We put the lines in. Lines are much easier to deal with than all those dots, right? So that is 3 shared pairs of electrons. There's 6 electrons there. Any questions so far? 9? No in German. Okay. Oop, there's extra electrons. Now there are some exceptions to this octet rule. You have phosphorus pentachloride. If you looked at this, pentachloride means there's 5 chlorines around there. That means there's 2, 4, 6, 8, 10 electrons around phosphorus. That shouldn't happen, but it does sometimes. That's the exception. Over here, sulfur hexafluoride, 2, 4, 6, 8, 10, 12 electrons around that central atom. Should not happen, but it does. There are just a handful of exceptions to the octet rule. Okay? We'll do VSEPR theory on Monday or Tuesday. Any questions about